but it wasn't recording. Now we are recording. All right, so everyone should grab the class1.inp file and the class1.dat file. And we are going to start today by looking at a basic latent growth curve model. In class today, we're going to go through 3 different types of latent growth curve models. Your homework is going to take you to a 4th different type of latent growth curve model that we're not going to cover in class as an example, but I'll talk about it. I'll talk about it at the very end. Don't let me forget, otherwise it's going to be incredibly confusing. It's not that confusing. Your homework is a dual process latent growth curve model, and so you will be looking at the growth of 2 different processes simultaneously. And has anybody looked at the homework, just out of curiosity? So it's written up as the Banner-Ross hypothesis. Yeah. And it has to do with gamma radiation exposure and strength. So anyway, let's talk a little bit about latent growth curves. Everybody has seen these before, right? So they look something like this. You have time points. 1, 2, 3, 4, and these are measured at some equidistance from each other, right? If you watch the video, then I talk a little bit about that equidistance. Then you have 2 latent variables, and these latent variables are based on these observed variables of time, right? And they represent the average level at any given time point, as well as the change from time point to time point. And so we call one the intercept because it's the average level and one the slope. And the intercept is all 1s, right? And the slope starts at 0 and then goes 1, 2, 3 in this case, right? When we have a categorical variable, a dummy-coded variable, and so for example, if we have age, we want to do a regression analysis and we have age, right? And we enter a categorical variable of sex in there, coded 0 and 1. And we get an intercept of 19.2 and a slope of 2.4. What does that tell us about age across men and women? You have to think all the way back to ARM 2. When we have dummy-coded variables, our 0 group tells us something, right? What is that in our 0 group?
The reference group?
It's the reference group, absolutely. In the context of regression, you have these 2 coefficients. You have an intercept and a slope. And the intercept in the equation that I just gave you was 19.2. And what does 19.2 represent?
Is the average level of the entire age of the population.
It's not the
average. Not the population, but the 0 code.
The 0 group, right? The average age of the 0 group is 19.2. If you were to center that gender variable so that it was at assuming you have an equal distribution of men and women, and you center it, and now gender is coded as minus 0.5 and 0.5 instead of 0 and 1, what does the intercept equal? Nobody knows? Let's do something. Let's pull something up here and have a look at it. I'm going to clear this. Go ahead. Somebody's going to say something. It sounded like somebody wanted to say something.
I'm just very excited to see
Oh, where is a good data set to use here? We could use one of our ARM3 data sets. Let's not use the exam 1 data set. What do we have in week 2? Well, we have BISBAS stuff. All right. Oh, that's fine though. Tab sex. All right, let's go center sex. Tab sex. Okay, oops, tab C underscore sex. All right, so there's obviously not an equal distribution of men and women here, right? We have more women than we have men, and so these are not minus 0.5 and 0.5, but let's do something. Let's go sum, instead of age, let's do BIS, okay? So our average BIS is 20.45491, and now let's go reg BIS sex. This is a regression model. Our average amount of BIS is 21.09635, and we have a slope of this. So if we go sum BIS if sex equals 0, we get this, the same as our constant, right? So in a regression model, like Jigs was saying, in a regression model, when we have a dummy-coded variable of 0 and 1, the intercept is always the mean level of the 0 group. And that means that this is what? What is that coefficient? What does that mean?
It means that if we change from 0 to 1, the age of the other group, which is not a reference group, but the focal group changes by this amount.
Perfect. That's exactly what it means. And in this case, we're not looking at age, we're looking at BIS. But so that means if we go, let's go DI, this minus this. Remember, regression analysis is just straight algebra, right? It's linear algebra. So that means that the effect of, or the level of BIS in the one group is 18.313039. We can check this by going sum BIS if sex equals 1, and it should be 18.3130. There's a rounding error there, of course, because that's the way that things go, but pretty dang close, right? You could also do, if you wanted to, gen r sex equals sex, recode r sex 0 equals 1, 1 equals 0. This is why state is nice, because you can just like very quickly manipulate all of your variables. You should all switch to state as quickly as possible. But now we can go back, use our same equation, and instead of sex, put in r sex, and what is our new intercept going to be? Now, sex is coded as 0 if you're a male and 1 if you're a female. So what is our intercept going to be? Perfect. 18.31304 or 31309, whoever, I mean, it's going to be there's a rounding issue somewhere in there, right? And what is our slope going to be? Positive 2.7831, right? Yeah. So, yep, there we go. It works out just the way that it's supposed to work out, 2.78 and 18.31. Okay, so what happens now if we use the centered sex variable? What is our slope going to be? So if we flipped around, go ahead. What?
Slope should be same.
Slope will not change. That's right. It will be the same as the one where 0 was females, right? Like obviously we're going to flip signs here, but so it should go back to minus 2.783311. What about our intercept? What's it going to be here?
0.
It's not 0. Let's have a look. It is 20.45491. Now that is not either of these. We had 18 and we had 21. Why is it 20.545491? What's going on here? What did we do with sex?
I think we reduced it to a 0.5 level below because
Well, we made the mean of sex. Remember, in a regression equation, you're multiplying a coefficient times a mean, right? And we made the mean of sex what?
less by 0.5.
We made it 0. We centered it, right? So the mean is actually 0 at this point. And so that means that the coefficient is going to be minus 2.783311 times 0, right? Plus the average age in the data set as a whole, which is 20.45491. So if we go sum, just BIS, 20.45491. Centering something sets it to the age, the average age across the entire data set. When something is dichotomized, it sets it to the mean wherever that 0 group is. This is important for categorical regression analysis, but it becomes incredibly more important for latent growth curve modeling because it means that you can move, when we look at our intercept here, right, what we're talking about is a whole bunch of 1s and then one 0 group, right? And so this is what the mean is relative to all of these 1s, right? Does that make sense? Is that clear as mud? What's going to happen then is wherever this 0 is, because these are all 1s, that's going to be our average. So let's have a look at this. Let's flip back over to M+. And so I have a couple of different equations here in mind, and I'm not sure what I gave you guys. Does yours look like I by blah, 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 S by blah, 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 I with S? Or does yours look like this, IS, T1, blah, blah, blah? Or does it have none of those?
That's some of this.
Which one does it have?
The two first lines in the model.
The 2 first lines? Okay, perfect. Let's do this. Just run these 2 first lines. You don't even have to have I with S. I'm gonna drop that. Let's do this. To start with, we're gonna come back to this discussion in a second, but I want to show you guys what's going on in a latent growth curve model when you are running it. So this looks like it should give us this, right? We have I, we have S, we hit run, and we should all get some sort of problems. Oh, actually, it will run. I'm sorry. No, you won't get problems. This should all run just fine. Is this what everybody has? chi-squared test 4.260, 3 degrees of freedom, p-value of 0.2347. Who does not have this? You're good?
Yeah, I was on the line.
Kelly, you good?
Yeah.
We're all good? Okay. As we scroll down here, we have a CFI, TLI. This model looks like it fits great, right? We have some intercepts here, T1, T2, T3, T4. And these are the average levels at each one of these spots. We have residual variances. We have variances of the intercept, variances of the slope. The problem with all of this is it doesn't actually give us the mean of our intercept or the mean of our slope, right? We need those. We need to know what the mean intercept is and the mean slope is. The way that we figure that out is we have to go back and change our code, right? In M+, how do we request a mean? Anybody remember? How do we set a mean to 0 in M+? Or how do we set a variance?
The variance is in the brackets, isn't it?
Other way around. Means are in the brackets, variances are out. So let's set a bracket. Let's go IS, end bracket, save, run. Now we should get an error. And I'm going to explain why we get this error. Yep. And it's giving us an error because there's a problem with that parameter. And the reason that there's a problem with this parameter is because in order to do a latent growth curve model, we have to translate these intercepts from each of these variables. They need to be pulled down here into the intercept and slope. And the only way that you can pull them, or maybe push them is a better way to phrase that, is to take this mean that would be here and set it to that. Set it to the fixed parameter. And so the way that we do that is we say that all of these means are going to be 0. And if all of the means are going to be 0, then the discrepancy between 0 and that mean gets pushed to the latent variable, right? So if we set that to 0 and now we hit run, we should have a good converged model. This is the long way, by the way. I'm going to show you the easy way. M+ makes this dummy proof. There is our model. Everything fits exactly as it did before. And now we get this. Our intercept is 0.523, and our slope is 1.026. So let's flip over and let's have a look at this. I'm going to clear this out. And arm 3, week 9, class 1. Let's go. So our intercept right now is set to what? If we look at our, so it is 0.523, and that should be what? Based on our model and based on what I was just telling you about. So M+ doesn't give us a line here that would be our 0 group. But if M+ did give us a line here, then this would be coded as 0. It doesn't give us a line because it's coded as 0. What is our intercept then? So it's right here. All of these are coded as 1. These are coded as 1, 2, 3. And technically this one should be coded as 0 going to this time point. So what is our intercept going to be? It's going to be what we just talked about in regression, the mean of our 0 group. Which group here has a 0 path going to it? I mean, it's not there, but trust me, M+ doesn't put it there because it's a 0 path. It's the mean of time 1, right? So let's have a look. We've got our means right here. Let's go sum time 1. We have 0.51417773, and M+ does a little bit of rounding. It's not going to be exactly perfect because this is also a, bear in mind, this isn't going to just be the mean, right? What M+ is actually doing, it's saying like we have time point 1, 2, 3, 4, and we have a slope and an intercept, and that intercept is going to vary a little bit based on slope, right? Like whether the slope goes this way or what. And so each one of these means is not going to be perfect, but it's going to be pretty close to the true mean of time 1, correcting for the little bit of changes in slope that you get with regression, because regression is not, and it's not, there is a y and there's a y hat, right? Like there's residual here. If it was perfect and all of these things and every point fit perfectly on this line, then your means would always be perfect. It would always be a perfect reflection of the intercept, right? But the same thing is going to be true here in a second when we look at what's going on with the slope. So the intercept is always whatever that 0 group is. Let's test that. We have a bunch of 1s here. Let's change this to -1, 0, 1, 2. What are we getting now? What will our intercept be? The mean of time 2. So let's have a look in Stata just real quick. Sum T2. It's going to have to account a little bit for the change in slope, right? But it should be about 1.57. Let's flip back over here, save, run. And what will our slope be? We've changed the intercept around. We've changed you can think of this as recentering time in the same way that we recentered sex, right? In the last, when I was just doing regression with the BIS. So we've recentered time. What will happen to our slope? Yeah, it should be exactly the same, should not change. But our intercept should be now 1.57 or fairly close. What about our model fit? Identical, right? We're not really changing anything. But now we can see our slope is now going from -1 to 0. This is where we're going to cross our line. If you think about regression in terms of this, right? Then you have -1, 0, 1, 2. This still remains your interslope or your intercept, right? So all we've done is shifted everything that way. And our intercept here is 1.549, and I said it would be pretty close to 1.57. It is pretty close to 1.57, right? Let's do the same thing. Let's move it all the way to the end. So this can be really important because if you do a study and you have some sort of intervention and you want to know what is the effect of this intervention at the final time point, right? Then you can move that intercept all the way to the end and it will tell you like, here's the average. And even better, we'll talk about this next week, you can then predict this based on group, right? So if this is your condition and you're predicting the intercept and the intercept is slid all the way to the end, then this coefficient winds up being the difference between two conditions at the end of your intervention, at the end at the last time point, right? So let's have a look at this. That piece will make more sense next week, but I just want you to realize that that's where we're heading. Let's change this to 0, -1, -2, -3. And now our intercept is going to be what? Sum of time 4, so it should be about 3.6. What is our slope going to be? Yep, we've recentered the slope, but it will not change. This line is going to be here. We're just moving this line this way, right? That's all we're doing. So now the same table would look like this. -3, -2, -1. 0, and you would have something along the lines of this, right? The slopes will be the same. We're just moving the table. All right, let's have a look. So we said the intercept should be about 3.6. And as we scroll down here, our model fit is exactly the same. Intercept 3.602, that is wonderful. So everybody understand what's going on with the intercept at this point? When you code the intercept as 1, then it will make your intercept be whatever that 0 group is within the slope, right? And in this case, it's wherever you decide to put it. You can move that wherever. And it's cool because it allows you to be really flexible moving things across time to look at, like, I mean, maybe you want to know what were the differences or what was going on at the midpoint, right? You can move the intercept to the midpoint. I mean, you can do whatever you want, and it doesn't ever affect the slope. The slope won't change. What is the slope in this? It's just basic linear regression, linear algebra. So what is a slope in linear algebra?
Change when you change from 0 to 1, what is the amount of change in the mean?
Yep. That's exactly right. What is the amount of change in the mean? And so we can calculate this really easy, right? Again, this is not going to be perfect because it's residual based, not a perfect fit, but let's do this. Let's go DI. DI just means display, by the way. This you can use Stata as just a calculator as well, and that's all I'm doing. So we have 3.60111 minus 0.514 blah 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 That is 3.0869337. And we have 3 time points. We technically have 4 time points, but when you think about time points, right, you have 1, 2, 3, 4. You only have 3 spots for change, right? And so you're going to divide by the potential rise over run, which is only 3 spots, right? In your on your linear thing, you've got the difference from here to here, from here to here, and from here to here. You've got a line that goes like that. So you've only got 3 potential rise over run differences, right? Does that make sense? When I use rise over run, I'm just talking, isn't that how we all learn basic linear algebra, right? Rise over run for your slope. I think that when they teach it, don't they teach it like, is it A equals mx plus b? Y equals mx plus c, is that what you said? Why do they do that? Why do they not do y equals bx plus I? Because then it would make so much sense, right? Then you've got a slope, which is always represented by b, and you've got an intercept, which is always represented by I. But yeah, they use these weird letters that make no sense to me, but whatever. All right, so we have this DI 3.0869337 divided by 3 potential change points, right? And we get 1.029. That should be pretty close to what our slope was. It's 1.026. Again, not going to be perfect, but it's pretty close, right? This is what's going on in a latent growth curve model. All it's doing is taking the average amount of change across the entire thing, dividing it by the potential change points to give you a slope, and fixing your intercept to be the mean at wherever you set that 0 group in a dichotomous type of scenario.
That's assuming change is happening at a constant rate.
Yeah, so we'll get there, but you're exactly right. This is assuming change is happening at a constant rate, right? The last thing that we're going to look at today is when change, or maybe it's the second thing. Maybe it's the second thing that we'll look at, is when change does not occur at a constant rate. And that's, of course, in regression, we call that what? Curvilinear or quadratic effects, right? And so we're going to look at a quadratic effect here in a bit. But I wanted to make sure that we're all on the same page looking at this piece of the model. The last thing are these means. So when we ran this analysis, we had to set this to be 0, right? And what that does is it pushes those means of every variable into the slope and allows the slope to calculate the differences in means rather than those differences in means being nested in the observed variables. It's less important if you use the fancy M plus workaround to look at this. So let's do the fancy M plus workaround now, which is, let's comment out this stuff. And let's just do this. So M plus knows that people like to do growth curve models. And so this is the code to run just a simple growth curve model. It will always fix your intercept to be 1s, and all you have to worry about is your slope. It will fix your means to be 0s, and we will get the exact same fit as we did before. Should I hit go? Are we all there yet, or not quite?
Yeah.
We're good now? I feel sorry for all the people not here today. This is one of the funnest, the best classes, right? Is the latent growth curve class. Poor bastards. I hope that they watch the video though. What's that?
No, that a few people are at a conference.
Yeah. I know that some people had emailed me and told me they were going to be at a conference. So. All right, are we good to go? All right, let's hit run. Our fit should be exactly the same as it was before. M plus gives us our little figure back there, unless you don't get it, which is irrelevant, I guess. And then as we scroll down here, there's all of our fit statistics, blah, 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 blah. Notice that M plus has now fixed all of our intercepts here because those intercepts get pushed down into the means. And here is our mean intercept and our mean slope and the correlation between our intercept and our slope. What does the correlation between our intercept and our slope tell us? This is important because all of this data is nested data within each individual person, right? So what does that correlation tell us?
With respect to like the group which is reference, if it changes to other group, how does the slope changes when we change?
Yes, so it's actually it's within each person, right? So this is a random, these are random varying intercepts and random varying slopes. And so what it's saying is, for people who start higher on the intercept, and in this case, it would be one value higher, whatever the value is, right? They have a steeper slope by a steeper standardized slope by 0.1. Actually, this isn't standardized. It's a steeper slope by 0.1333. So if your intercept was 0.52, then your slope will be 1.026. If your individual intercept was actually 1.52, then your slope will be 1.159, right? Assuming that the scaling here is 1, which I think it is. But yeah, so it's saying like the higher your intercept, the steeper your slope, and vice versa, right? The lower your intercept, the more level your slope. Yeah.
I'm lost.
Okay. So let's start with the intercept, right? We'll walk through the 3 important pieces of information that you can glean from this model right here. 1, at the get-go, the average person is at 0.52, right? When they started, 0.523. The average person changes by 1.026 across time in a linear function from time 1 to time 4. Not everybody changes by 1.026, right? And not everyone is at 0.523. Now, we look down here, we have these variances, right? This is the variance of the intercept and the variance of the slope. That tells you how much people are varying away from that intercept and away from that slope. When you see people plot these things out, right? And I put a figure of this in the video. You see it's actually doing, we have 500 people in this data set. That means it's calculating 500 different slopes, right? And so we have an average intercept of 0.5 and an average slope of 1.026, but we also have people who look like this and this and this and this, and they have intercepts up here and intercepts here, right? And then on the average, we get 1 intercept, or 1 slope, and 1 intercept. But we have variability around this intercept and variability around this slope, right, for each person. And if your variance is down here, if you run a model and you see that your variances are, let's say for the intercept, you have a variance right now of 0.989. What if that variance was 0 and it was non-significant? What does that tell you about your intercept?
Everyone has the same intercept.
Everyone starts at the exact same spot. Absolutely. If your variance right here was 0 and your p-value is non-significant, what does that tell you about the slope?
Everyone's changing at the same rate.
Everyone changes at the exact same rate. It is not uncommon to have a lot of variability in the intercept and no variability in the slope, because oftentimes the relationships that we see are fairly constant across people, right? So you might see constant change across time, which means no variability in slope, but a lot of variability in where people started out, right? Does that make sense? In contrast, you might see that everybody starts out at the same spot and everybody changes differently across time, right? So you could very easily have a situation where there is, or maybe you see no variability in either, right? So those are your options: variability in an intercept and none in the slope, variability in the slope and none in the intercept, variability in both, or variability in neither. So that's an important piece of information that you can glean from this. What that correlation between the intercept and slope says is, based on where you start, will dictate how you change across time, right? So the higher your starting value, the steeper your slope will also be across time for each individual, right? It's broken down by individuals. Does that make sense now? So if a person starts at 0.5, their slope is 1.02. If a person starts at 1.5, their slope should be, assuming that our scale is 0, 1, 2, 3, 4, 5. If a person starts at 1.5, their slope should be what? Anybody? What brave soul wants to take a guess at that?
It's a question.
Okay, so if your slope is 0.523, or I mean your intercept is 0.523, which matches the intercept of the overall data set, then your slope is going to be 1.026, right? On average. If, in contrast, your intercept is 1.523 instead of 0.523, what should your slope be on average?
Would it be 2.026?
No, not quite.
What's the correlation?
There we go. Thank you.
So it's correlation multiplied by 1 point.
It's not multiplied. It's just added.
Multiplied.
You just add it. Yep. Yeah. So your new slope, because if you move up by a value of 1, remember it's just linear algebra. You move up by a value of 1, then this value moves up by 1.33. So your new slope winds up being 1.159. I'm sorry. Your slope gets steeper as your intercept goes up, right? In contrast, if your intercept is 0.023, it's decreased by 1/2 of a metric. What is your slope?
Is it 0.95?
Yeah, 0.95 roughly, 0.96, something around there, right? You're subtracting half of 0.133 because you've moved down by half of a thing. That's exactly right. Your slope becomes less steep, right? Yeah. Does that make sense? Who is completely lost right now? Not completely. Who's a little bit lost right now?
Well, my thing is like, so I understand what you're saying, but I guess conceptually, why are we using the correlation as like that? Like, why are we subtracting and adding the correlation?
Well, I
Like,
just.
what about the correlation is, you know what I mean?
Why is it important? For the most part, is that what you're
Like, is
asking?
that like is your correlation like an effect size here? or
So
something, or-
what the correlation is telling you is that where a person starts dictates where they end up, right? And it dictates how because the slope is not constant. A person who starts higher is going to wind up in a different spot than a person who starts lower, and that spot won't just be the difference between where they started. It will be the difference between where they started plus whatever the difference is between the plus 1.33, basically, right? Does that make sense?
Yeah.
It's almost never spoken about. Like, people don't talk about it. They'll say like, so in a paper you might say like the correlation between the slope and the intercept was 0.133, which means that people who started higher, individuals who started higher had a steeper slope or something along those lines, right? It's important to know. It might be especially important to know if you're doing some sort of an intervention where change might be dictated by where you initially start, right? Like, if everybody changes at a constant rate, if there's no correlation between intercept and slope, then everybody changes at the same where they start, right? But that isn't always, in fact, almost is never the case. So it's usually just worth noting. I don't ever see it as being like the main issue in a paper, but I think it's important to note that sometimes where you start dictates not just where you end up as a function of the slope, but the fact that that slope becomes steeper or less steep based on that correlation. Right? Does that make sense? I feel like I just made it more confusing. All right. So we have gone through, we have looked at doing a latent growth curve model. We have evaluated the intercept and we have evaluated the slope. And then we have slid that intercept around so that you could see the intercept is really just the mean, the rough mean, the approximate mean, right, controlling for the slope at any given time spot. And then we talked about the relationship between the intercept and the slope. What questions do we have over the very basic linear growth curve model? None? All right, then let's take a break.
Can we,
Oh.
look at the input for a second?
Yep.
Just, I think I missed something in my model. Gonna fix that.
Okay. But